Hey, it's Joel Duff. Welcome back. The Dead Sea Chronicles, Part 3. This time we're talking about the whole Jordan Valley, a land that's literally being torn apart. Right? Part 1, we just gave a big survey of this 12-part series and some of the things that we are going to be talking about, mostly the origins of the Dead Sea. Second part, we talked about some features of the Dead Sea itself. Talked about how far below sea level it is, over 1,400 feet below sea level. We talked about how it's going lower and why it's going lower. Talked a little bit about its future and a bit about its recent past, last couple thousand years. But now we need to get down to this really crucial question. Where did the Dead Sea come from? What is its geological origins? Why is there this deep gash, right, in the earth running north and south, which we call the Jordan Valley or the Dead Sea Basin or the Dead Sea Transform Fault, which is the more geological term for it? So we're going to dig into some of that geology and look at the origins of the opening up of the land itself, which allows this basin to form, which at the bottom of this basin, we find the Dead Sea. So let's get to it. We noted last time that we have a eyewitness account of the Dead Sea from a little over 4,000 years ago. And that eyewitness account comes from Genesis 13, in which Abraham and Lot are looking out over the valley of Siddim, or the valley of salt. And what did they see? Well, they saw something similar to this. Of course, you see occupations there now. They saw occupations then as well, though not these modern ones. But what's most important about what they saw is they looked around, and Lot looked around, and he saw that this whole plain of the Jordan Valley above the Dead Sea, right, or north of the Dead Sea, was well watered. All right. Now, this is a well-watered valley right here. This isn't a tropical valley by any means, but it's well-watered in the sense that there is water sources available. The Jordan River, along with a number of springs that keep a constant supply of fresh water to this area, allowing for irrigation. Right. So the biblical evidence, right, from Genesis 13 indicates that at the time of Abraham, there was a valley. All right. A long valley with a river at the base that provided irrigation for the plain around this Vale of Salt, all right, the Salt Sea. And like the Nile River in Egypt, the Jordan River creates this lush oasis. What to them would have at the time and today, as you can see on the walls of this valley, right, it's a forbidding desert. So the description from Genesis is not too far off from what we're probably seeing today. And other depictions of the Dead Sea in the Bible and other texts provide a picture of a deep rift valley, a rift valley that's familiar to us again today. There's natural freshwater springs, there's a lake of salt, there's a mountain of salt with caves in it, there's tar oozing out of the ground, there's natural pits in the valley floor. We're going to talk about sinkholes a little bit later on. And so all of these features, which are made mention of in the Old Testament in various different places, are features that we can observe today in this area, right? And that gives us a picture of the Dead Sea from the Bible, of a place that's already established with what we would consider modern day characteristics. But of course, our big question then is, how did it get to be this way? How did these features form? Well, did they look different farther back in the past? Or has it just simply always looked this way since the beginning of time? Was the Dead Sea and this area and the features of this area just instantly created by some supernatural means? Or is there more history here than we have in our written annals? So we've explored the recent history of the Dead Sea, and we've looked a little bit about what the future may look like. That was the last episode. But these geological features, I would say, have a little bit more of a story to tell. Right? I don't think they've always existed, right? Into infinity, they have an origin. They have a beginning point. The Dead Sea surely wasn't always as it appears as it is today. The Dead Sea surely has not always appeared exactly this way. We know that from the sediments that are contained underneath the Dead Sea, which is a future episode. Today, we're just looking at the ancient origins of this rift which is the ultimate cause of the scar that is this north-south valley. So have you ever wondered what it would be like to stand on the edge of two continents? To place one foot in Africa and the other one in Asia, or in this case, maybe better put in Arabia or the Arabian plate, right? This part of the Middle East it's literally being torn apart right now, right? There are geological forces at play that are moving the land and creating the features that we see today. Now, of course, these processes are occurring much, much slower, right? At a glacial pace, right? Compared to, say, like the political upheaval we see in this particular region. But nonetheless, it has done much to sculpt this region over the many millennia and produce its geographical characters that we associated with the Promised Land and all the features that are recorded in Scripture for us and other ancient Near East texts. Tell us about these geographical characteristics, which we then identify, all right? The wilderness of Judea, the Jordan River, the Dead Sea. And what do they owe all themselves to in terms of their origins? Plate tectonics. Now, we're gonna get to the whole young Earth creationism and those who believe the world is very young, and they have a way of trying to understand how these were formed, but they're going to appeal to plate tectonics as well. So, but we'll get to that. That's coming up. The Dead Sea isn't just some simple valley, right? There's a lot of valleys in the world. It really occupies a very deep gash in the Earth's crust, which is known as the Dead Sea Transform. This transform fault system is a plate boundary. It separates the Arabian plate to the east from the African plate, or more specifically, a portion, a piece of the African plate called the Sinai subplate to the west. It's part of a much larger fault system that extends 1,000 kilometers all the way down through the Red Sea to the south, and then up to Turkey in the north. And you can see that on this figure here. And so the fault, right, a fracture in the sedimentary, the geological column that runs all the way here from Turkey, all the way down here to the Red Sea. And these arrows are giving you an idea that it's sliding up, right? That the rock is, that this plate, the Arabian plate, is sliding to the north or slightly to the northwest. And the African plate is sliding to the south. It's really staying fairly stationary, and the other one's kind of the one that's sliding up. In the Red Sea, you essentially have a new ocean ridge there, where the plates are separating apart from each other, right? You have heated mantle that's pushing up and then pushing out, and that's pushing apart the Red Sea. So the Red Sea is actually getting wider all the time. And then that fault, as it gets wider, it pushes up, and all this rock is sliding past each other. So let's just step back for just a moment. Let's describe a transform fault. I mean, you have to first imagine there's two massive pieces of the Earth crust, and those two massive pieces are sliding past each other, kind of like the San Andreas Fault in California. All right, that would be a simple fault, just, they're moving, sliding past each other. And when they lurch, right, they don't just slide constantly. They're sort of like take little steps, a couple feet at a time, maybe more sometimes in a large earthquake. Then they kind of are resting, building up tension, and then they release that tension and move again. But there's still sort of an average amount of motion per year, because the entire plate has this stress and it's jockeying for position with the other plates. So it just means if you stand on one side of the fault and you look over, and you should be seeing the other side moving off to your left, right? To in this case, to the north. Well, of course, you're not really going to see that during your lifetime unless there is a very significant earthquake that occurs, in which there's a release of tension that's building up, and then suddenly there's a lurching motion in which there's an advancement of that rift, all right, the plate in one direction. But the overall pace of the movement of these plates is excruciatingly slow, right? In terms of our lifetimes, right? We're talking about usually millimeters per year. And this motion has been going on presumably for millions of years. And we'll get to, like, how do we know that that's been happening for that long? Or how do we estimate how fast the plate has been moving long ago versus today? And so as it's doing that, it's just gradually tearing this landscape apart and creating this distinctive rift valley that we see today. So, but in this case, you might want to look, okay, well, so it's sliding past each other, but what about other faults in the world where you don't have the land falling down? Well, that's because there's a little something else going on here. The Arabian plate, and we'll see this in a future figure, but the Arabian plate is moving off to the northwest. We have southern motion of the African plate. And then the Arabian plate, though, is kind of moving, but also shifting because it's being affected on other sides as well. And so it's kind of torquing. And as it torques, it's not just sliding to the north, it's also kind of moving a little bit, not directly north, south. And so therefore it's pulling apart there. All right. It's gradually pulling it apart. And so as the land is pulled apart, right, and fractures form and additional rifts form, then the land in between is going to fall down. I got a whole series of figures that will illustrate this. This particular rift, Arabian plate motion in this particular area along the Dead Sea Rift is estimated to be moving. Well, actually, I shouldn't say estimated. I should say actually measured to be moving 4 to 5 millimeters per year. Okay, so what I'm going to show now is I'm going to show a series of illustrations that I have created that are very simple, but represent the overall, like the big picture of the geology that's occurring here. And then eventually what we're going to do in other later parts of the series, I'm not going to do it so much today, is we're going to look at and we're going to compare models, right? We're going to compare what I'm going to tell you about the conventional model of the origins of the Dead Sea. And then we'll compare that with the young Earth creation model of the origins of the Dead Sea to see where there might be similarities and where the dramatic differences lay. So if we go way back in time, and from a conventional dating perspective, this would be some 20 to 25 million years ago. You had this area, right, which is the Palestine area, the Levant region, right? And at that time, there was a stack of rocks, right, that just covered this whole area, relatively flat, right? Not really any mountains in this area. You have your basement rock. And you think of your basement rock as that's your continental crust, right? That's your continental crust made of granites and just like there's no fossils in here. This is the original rock of the crust of the earth. And then on top of that, you have layered sediments, all right, or layered rock in this case now. A number of different kinds of rock, but all found in layers, right? There might be layers of volcanic material, layers of chalk, there's layers of clay or clay stone and siltstone and so forth, right? So there's a number of different layers in the Paleozoic, which I don't have the timetable on here, but these rocks would be 500 million years old up to 270 million years old or so. And then you have the Mesozoic, famous for the Triassic, the Jurassic, and the Cretaceous, which are the age of the dinosaurs. And then you have that ending at 65 million years. And then you have some Miocene rock on top of that. And for those of you who have good knowledge of the geological column, you'd be like, oh, there's something missing there, all right? Yeah, there is a chunk of rock that's missing between the 65 million years and like 30 million years ago. So that's a time period in which it's thought that there was no deposition in this area. So this is mostly a lot of types of marine rocks. And then there's a gap there, and then there's rock from the Miocene. And I need to provide some context here. West to east. Think of this as Jerusalem over here and then Jordan over here. And what we're doing is we're looking at a cross section through the Dead Sea region. But the Dead Sea doesn't exist at this point, right? There's no valley here. So there's no canyon, there's no river, there's no Jordan River, and there's no Dead Sea, right? You have a relatively flat piece of land, not very far above sea level at this point. And so that's about 15,000 feet of sediment that are on top of the crust. Now, if you're thinking ahead, you're thinking, young Earth creationists would say that, all that sediment came from Noah's flood. So if you're a young Earth creationist watching this and you want to think about how am I going to explain this, think about these different stages of what would have happened and when you think that might have happened. All right, so there's stress that builds up, right? There's a lot of pressure, right, going on because, for as long as we know, there have been continental crusts and ocean, and there's been plates that have been moving around, and as they push in against each other, right, that creates more pressure, which causes other interactions, right? And then there's new ocean forming, pushing out, and that's pushing into the land or pushing underneath the continents, right? Creating volcanoes, all that kind of stuff that goes to plate tectonics, right? But at least for this local area, you did have the Mediterranean Sea out there, and you had the Arabian Peninsula, right? And this piece of continent now is attached still to the Asian plate, right? The Arabian plate is still attached to the African plate here. It wasn't two separate plates. But because of what's happening in Africa, what's happening in the Middle Eastern region, there's a lot of pressure there. All of a sudden, it's cracked, right? All the way down through, right? All the different layers, that 15,000 feet and even farther below down into the basement rock. Because eventually what's going to need to happen is this whole thing's going to have to split so that it can start sliding past each other to relieve that pressure. All right, so you go a little farther forward in time. Let's just zip forward a few million years. And because of the torque of the Arabian plate, the African plate, right, sliding and pulling and twisting, then what you have is you have additional faults that form. Right. And those faults are, basically they're additional cracks along where the original crack is. Right. And as this twist begins to occur and they're all helping to slide past each other, right, that begins to open up a wedge in some areas because of that torque. And so because they start to pull apart. Right. And as they start to pull apart, there's also some upwelling below. All right. There's a magma below in the mantle that's basically pushing up. You got a weak spot right here, and potentially it could push up enough that magma could come all the way up to the surface, right? Which does actually happen at basins. I'm going to show you one in a few minutes. And so as that's pushing up, there's going to be this is what's going to be complicated about this. It's not just sliding north, just sliding past each other. It's sliding, torquing, and lifting. And one side gets lifted a little bit more than the other because, of course, they're not attached to each other anymore. So one side could, as much as it's sliding to the north, it's also uplifting on one side more than the other. That gives you this high plateau on the east side of the Dead Sea, which the plateau isn't nearly as high on the west side. Right? So there's an unevenness to the valley too. That also needs to be explained. I mean, anybody that goes to that region and sees like, hey, there's a really high mountainy looking things on one side, not so high on the other side. How did it get that way? Right? Sliding and lifting. And so what happens is you have, it's sort of the whole area is lifting up, but more importantly, the section that's between the two main rifts, right, which is called the Dead Sea Fault, the original fault, and the Gore Safi fault, as they pull apart, well, if you pull apart, then what's between, right? There's a gap there, all right? And so the rock that's between, the section in between starts to fall down into the wedge, right? And as it falls down, it's the beginnings of a basin. That's the formation of a basin right there. And as the basin forms, of course, material is going to erode off the sides of these now walls on either side of the basin, and it's going to start to flow down in there, right? So streams are going to start to form, the erosion patterns, and then you're going to start to send sediment down into the basin. Of course, the basin's going to start to fill up with sediment. Now, if it falls at the same rate the sediment comes in, then you're not really going to see the basin look much lower, right? It's going to look like it's not that deep, except that sediment's constantly piling up. So the sediment just keeps getting higher and higher and higher in the basin, but the basin keeps falling. What's happened with the Dead Sea, you can just think a little bit farther forward, it's like what's happening with the Dead Sea is that the basin has fallen at a faster pace than erosion and sedimentation can fill up the basin. That's why it's below sea level, right? The whole land started above sea level. Then a basin starts to form, and this center region starts falling through, and then this basin keeps getting deeper. Additional faults form, and it just because you still have the torque going on, and you still have new cracks forming, and now they're just starting to fall down, falling down into the earth, right? And so as it does that, the basin gets deeper and deeper and deeper. But there has been an enormous amount of sediment that has filled up the basin, most of the basin, right? We have, 10, 15,000 feet of sediment. And one of the most important forms of material that's filling up the basin is salt. Salts of various forms. You can think of like sodium chloride, halite, as one of the primary ones that fills this particular basin. All right, so the uplift continues. And what I also need to show you on this particular figure is that the one side, the east side, is lifting at a greater rate than the other side. So you see the Miocene over here, rock? That rock now is lifted up higher. And in some cases, it's eroding off, right? It's getting eroded because it's being lifted up. And therefore, it's becoming this high plateau, which is being eroded. And eventually, much of the Miocene material is completely eroded away. But this continues to lift up, which is why there's still higher hills, right? Higher mountains, a higher plateau. It's really kind of a plateau that drifts, a plateau that's sort of warped up. And this continues to fall. You have the Pliocene rock, that's a certain age of rock, all right? That's 2.5 to 8-10 million years or so. So this is millions of years worth of salt that's laid down on the sand. Then you have the Pleistocene, which is much more close to the present. And eventually you get to the Holocene, which is our present age, which is only the last 10,000 years. All right, so here he's showing that like now we have the Miocene, Mesozoic, and Paleozoic has dropped all the way. And we know this from various kinds of surveys and drill cores and so forth that have gone down there. Some of it's reflective patterns and ways that they look for oil and so forth, right? So we have an idea what the internal structure below the Dead Sea Rift is. And we actually have drill cores that bring up the sediment columns. So you have to go way, 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 way down, all the way down more than 15,000 feet before you reach the Miocene rock. Whereas if you're over here in, Jerusalem, you got Miocene rock, a little bits of it still left around, which are on the surface, right? And then you just go a few miles over there and it's like, wait a second, that's 15,000 feet down from where we're at now. That's a huge drop. So this is a lot of rock that has fallen a long way down. And on the other side, you can see like this has continued to push up, right? All this area has been lifting up to the point where the Miocene is gone. And now it's really the Mesozoic rocks that are sort of up there. And even in some sense, I think that much of it's the basement rock is visible on the sides because it's been pushed up so much. All right, so this is sort of like today's snapshot. And where is the Dead Sea? The Dead Sea would just be a little blip right here at 1,400 feet below sea level. And so the point here is that although it seems very dramatic and the valley seems very dramatic, being 14,000 feet below sea level, but then also mountains or this plateau sticking up another couple thousand feet above it, as we saw in the previous episode. Even though that's the case, there is far more material below the Dead Sea, below the whole Jordan Valley. In fact, we're not just talking about the Dead Sea. We're talking the whole Jordan Valley is dropped down. And so there's this huge, enormous amounts of sediments below it. And those are the ones that we're going to be talking about a lot because we need to figure out like how they got there and how long it took to get there. There's another feature I want to show you here briefly, and that is the Mount Sedum salt diapir. And that is a large amount it's basically a salt mountain that has been squeezed. Well, salt has been squeezed from 15,000 feet below, and the weight of the sediments above it have basically caused the salt to move almost in a flowing, a liquid motion. All right. Very, 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 very slowly. Okay. But the salt can't handle the weight on top of it. All right. It's not strong enough for that. And so it has gotten squeezed over to the west side of the valley and then gotten pushed up and squeezed out onto the surface where there's this huge mountain of salt at the base or at the south end of the Dead Sea. And so we'll have a whole episode just on that. Mount Sedum Salt Mountain. So you probably should be thinking to yourself, I mean, how do we know all this stuff? How do I know that what you're telling me, Dr. Duff, has any basis in reality at all? In particular, the motions of the plates. You mentioned it's 4 or 5 millimeters at a time, and that this has been happening over long periods of time. I didn't stress this too much, but we're talking about 15, 20 million years of motion of this rift. Right, so the rift begins, it slides north, and then it starts to open up, and then you have this falling action. This would be, it's falling by a few inches a year on average, right? So it's going to takes a long time for it to make its way all the way down 15,000 feet below sea level in terms of where the bottom, the true bottom of the Dead Sea is, on top of the Miocene rock that's way down there. And so what we can see from this map is here's some current plate motions. Now, when I say current plate motion, these are measured, all right, actual measurements, because we have satellites that are constantly looking at all the plates, and there's particular places in which you basically ping back and forth, and you constantly see where exactly that position of the Earth is at one moment in time. And next year, it'll be in a different spot, right? Because all the plates are in some motion. Some are near standstill and everyone else is pushing around them, but nonetheless, most of the plates are experiencing a motion in some direction, and these arrows are indicating the direction in which in this case, the Arabian plate is moving. And the length of the arrow indicates the amount of motion. All right, so like this much down here is 10 millimeters. All right, so this is more than 10 millimeters. There are plates that are moving at 50, 60 millimeters a year, very, very rapid pace. But this motion down here, you see the Dead Sea Rift? It's actually, the Arabian plate is actually kind of, again, it's moving this direction, but it's also moving this direction and this direction. So the whole thing is kind of turning, and that's what's creating an incredible amount of stress over here in the Dead Sea transform fault. That's why it's pulling apart there, creating basins here. Whereas you don't get basins over here. It's just pushing up against another continent. And up here, you have it pushing, and there's actually mountain formations in the north along up in Turkey. This other figure over here shows just how complex the plate motions are. I mean, you have Turkey, which experiences a lot of earthquakes for good reason. They're surrounded by a bunch of faults, and it also is under a tremendous amount of stress. I mean, Turkey is pushing south over here. All right, there's a plate that comes out to this line here, and you can see some of these lines are pretty long, right? It's moving pretty quick and pushing along this direction. But it's up here, it's pushing this direction. Up here, it's kind of pushing out. That thing is just being twisted. Turkey is just being twisted. And so it has lots of contacts and lots of rifts in which there's a lot of pressure that builds up and has to be released. And that's going to be released in the form of earthquakes. So how do we measure these motions of entire continents? I gave you a quick example of like really modern technology of basically satellites watching us. That means that GPS is doing that, right? You have something in your pocket, right? The cell phone that does not have the capacity to be that precise. You're not given military grade precision GPS, in your devices. But if you were given much better precision, you should be able to, measure your position exactly on the Earth, and then measure it a year from now in that exact location and be able to see that it has moved, right? You have moved to a different spot over that time frame. So GPS has provided us with really one of the most amazingly accurate measurements of plate motion in this particular region. And that's how we know just how much each one of these is moving. So 4 to 5 millimeters, I know that doesn't sound a whole lot, but if you add it up over millions of years, then you're talking about, 65 miles of motion. I'm sorry, I think it's 65 kilometers of displacement that have occurred along this rift, which also means that, and one of the reasons we know that has happened is that, let me see if I can use this chart. A rock that is right here in the Arabian Peninsula. I'm sorry, the Sinai Peninsula, right? If you have layers of rock here, let's say there was a particular volcanic eruption, which there are in these areas, and it laid down volcanic material that crossed over the rift, right? And if it crosses over the rift at some point, or like maybe before the rift actually formed, right? So 20 million years ago, and there's a big blob of radioactive material. Let me get a pen out here. So you have volcano, and it creates a whole, like a little area of magma that solidifies, and that's crossing over the rift. And then when the rift forms, what happens? This particular rock is going to get dragged north, whereas this lava over here is going to stay where it is, essentially. It's not really moving south very fast, very much at all. And so eventually you end up with 60 kilometers. How do we know 60 kilometers of displacement has occurred? Because today those rocks that are the same lava as this lava down here, they're 60 kilometers away from each other, right? And you can test the chemistry of that material and say, like, yeah, this came from the same volcanic eruption. So how could they be that far away from each other? Oh, well, there's this rift between them, and the land has been moving, and it's just literally like a conveyor belt, and it just moved that rock north. And that brings us to a way in which we can estimate how fast the plate has been moving in the past. Thousands of years ago, hundreds of thousands of years ago, millions of years ago, right? Because if you date the lava, right? You date the magma with radiometric means, and you get a value that says, hey, this is 5 million years old. Well, if it's 5 million years old, and what does it tell you? It tells you 5 million years ago, these two rocks, the rock on this side and the rock on this side, were right next to each other 5 million years ago. Today, they're 60 kilometers apart. What's 60 kilometers divided by 5 million years? You're going to get a rate. Here's on the average how much it moved per year in order to transport it that far. And here's the amazing thing about that. I keep saying that because it really is amazing, right? If you look at that, if you do that kind of analysis, radiometric dates of materials from when they originated next to each other before the plate, before the rift, you end up getting very close, if not nearly statistically the same value as satellites are measuring today. That tells you that rift has been moving, right? The plate has been moving at about the same pace over all that period of time. Yeah, I was going to talk about paleomagnetic studies as another way to estimate plate motion from the past, but I'm just going to suggest you read about that in my write-up for this particular section, which is on my blog. Right, that'll have much more extensive explanation of some of these things. But I want to focus on the interesting data here, and plate motions estimated from radiometric dates versus laser measurements. So another way you can put lasers. You can put a laser going across where a plate boundary is, right? And then you just constantly measure, or you measure every once in a while, the distance between the 2 points from the laser and the receiver, right? And you measure how long it takes for the light to bounce back and forth, right? And that'll give you a way to calculate how far apart they are. And so if you have continents that are moving apart from each other, then you get an estimate of the right. You really can just, GPS today kind of does that in a more simple way for us. But anyway, laser measurements have been done across lots of different places on Earth to get very precise measurements of plate motions. And so then they've also estimated the same plates and their motions in the past, right? Using radiometric dating of rocks and looking at displacement and using this paleomagnetic thing, all right, where you can get dates as well that way. Right. You put those two together and you get an estimate for the number of millimeters per year the plate has been moving, estimated over like from 30 million years to 50 million years ago. Like how fast was the plate moving? Or like 20 million years ago, how, for 10 million years, how much was the plate moving? Because you can get multiple different dates and you can calculate the times between them. And you can ask, what about the entire time? What about from 100 million years ago to today? Really, usually it's like 40 or 50 million years ago to today. What's the average? And then you can ask, how does that average work with the actual measurements in which we have determined an average by studying it for the last 10 years? And you get a figure like this, which is just a remarkable convergence of these dates because they fall on a line. And what I mean by fall on a line is this. If you have a measurement based on satellites, all right, and lasers, and your plate is moving, and your estimate is it's 50, all right? It's moving 50 millimeters per year. So there are some plates that are moving 50 millimeters a year. And this dot right here, that would be that dot. And then you do the same dating, you do some, well, not the same dating, you do the dating for that particular plate, but using a different method. And you discover, oh, it's been moving on an average for the last 10 million years of 50 millimeters per year. Since those two dates are the same, that's why this dot is right here, finds itself on this graph at that position. Then you can ask, okay, so that's one point. Because like, well, that could just be a coincidence. It could be a coincidence that you just radiometrically dated some rocks and you divided by the number of years and the distance that those rocks are from each other. And, well, I got the exact same date or very similar number than my, lasers got, which are measuring it to today. So today's measurement and yesterday's measurement, yesteryear's measurement, they're the same. Pretty cool stuff. Gets even crazier when you start looking at other plates and you find out, well, some plates were 150 millimeters a year. Oh, well, guess what? The radiometric dates also suggest that 10 million years ago it was moving at 150 millimeters a year. And then other plates are moving in, actually they're moving toward each other. All right. So that's why the negative numbers, by the way, in case you're looking down there, it's like, yeah, they're moving toward each other, right? So they're getting closer together. And the past estimates suggest, yes, they were getting closer together at that rate. And they're getting closer together this year at about the same rate. And so for most plates on Earth, it appears they've been moving, at least for the last 10, 15 million years, at about the same rate that we measure them moving today. That's either an incredible coincidence or it is very strong evidence that the Earth has been undergoing the same types of actions. All right, the plates have been moving and acting in the same way for very long periods of time. All right, another quick example of this, just to give you the idea of how we would do that. Here's one of the most famous tests of using radiometric dates and looking at how far the rocks have moved over time to calculate how fast a plate's moving. So the Hawaiian Islands sit on a plate. All right, they sit on the Pacific plate. That plate is moving away, all right, from California. And if you take a look at remember the Hawaiian Islands. So remember the highlands, the main island of Hawaii down here, the biggest one. Right here is where the active volcanoes are, right here on the end. Right, so that's where the hot spot is, where stuff's welling up from deep in the mantle. And it's producing a volcano. In fact, there's a new volcano forming underneath the sea here, which will become a new island someday. Right, but the plate is moving in this direction. Right, so what happens is that after a while, this island, even the main island here, has moved away from the hot spot. And now the hot spot is on this end of the island, and then it will continue to move away. So these islands potentially, the original hypothesis, all these other islands in this long chain, maybe those islands at one point were back here over the hot spot, and they simply have been moved away because the plate they're sitting on has slid over, right, away from its source of magma. And maybe they've been doing that for a long period of time. Yes, the evidence suggests that's the case. Because if you go 1,000 kilometers away, all right, you go down here and you say, I look at an island that's 1,000 kilometers away, and I figure out how old it is, radiometric age. All right, the radiometric age is, I go up here, I go over here, and it's like, oh, the radiometric age is 12 million years. All right, and then I go to 2,000 kilometers away, and it's 21,000 or 21 million years, and 3 kilometers away, and so forth. You get the idea. The islands that are closer, you date them, and they're younger. So these are the radiometric dates that have been measured. Right? And they follow along this line. And if you take any one of these dates and divide by the distance, right? You just divide by the distance, you get how fast the plate's been moving over that period of time. And what you get is you get something like 8.5, 8.6 centimeters per year. Right? That's 86 millimeters, by the way. So this is a pretty fast moving plate. That's how fast we measure it to be moving by GPS today. So it's moving that rate today. It seems to have been moving that rate for the last 10 million years, 20 million years, 30 million years. Then when you hit 40 million years, the rate is actually slightly faster. The slope is a little bit different. So that suggests to me the plate we think the plate actually bumped into something and started moving in a different direction. Oh yeah, you see how there's a bend right here? That bend right there, that plate motion was different in the past, a different direction. It's not surprising it was moving at a different pace because it had different stresses on it at that time. But the point of all this is incredible coincidence if these islands, in fact, are not millions of years old. Right? You might say to yourself, I don't believe radiometric dating. Right? It's highly suspect. There's all kinds of problems with it. I don't trust those dates. But why are the dates at all, why do they show a pattern then? They show a pattern of resulting in the same estimated rate of motion from 50 million years ago as we measure today. And those two numbers were independently derived. When you independently derive two estimates that are the same using different methods, it's very strong evidence, right, that those islands have been slowly and incrementally being moved away from the hotspot at a constant speed for 20, 30, 40 million years. Now, I tried to say earlier that the Dead Sea Rift isn't just about horizontal motion. The rift is also experiencing pretty significant vertical movement. I think you can see some of this vertical rise here. So you're looking across the Dead Sea toward Jordan, and over here you have what look like much higher mountains, but they're kind of actually a large plateau on the top on the other side of that. This is mostly caused by erosion of this land being lifted up so much, and now you have erosion of material into the Dead Sea Basin. On this side, the side where the picture is taken from, it's not nearly as dramatic. I mean, there's a good rise over here, but it's not as much as on the other side. And then when you consider the types of rocks in these particular layers, these layers at the base right here are virtually, I can't remember exactly if these are basement rocks, but they're very, very old rocks. So they represent the lowest members of the sedimentary column or the geological column. Whereas on the other side, the rocks that are on this side are buried underneath still, right? They have not been raised up like that. So as a result, it's not just the land under the Dead Sea that's shrinking. I need to emphasize again, the entire Jordan Valley, all the way up north of the Sea of Galilee, the whole thing has been falling down, right? It's all sinking, and it's taking it farther and farther and farther and farther below sea level. There's more than 2,000 feet of water in the deepest spot in the Dead Sea. And so that does represent just how far the bottom of the Dead Sea has fallen. So 1,400 feet plus another 2,000 feet, 3,400 feet below sea level. And it's still dropping at a pace that's probably faster than it's filling up with sediment. And so the future suggests that it's just going to get deeper. The basin is going to get deeper. Now, the Dead Sea Transform is a pretty unique place. But it's not the only rift system in the world that behaves in this fashion. In fact, there's quite a few other similar rift zones that are continental rift zones, such as this one, the East African rift system, which isn't too far away. We were all the way up here, But if you come down here into the East African Rift System in Ethiopia and Kenya, what you'll find is that you have plates that are pulling apart, right? We're going to form a new ocean here someday. Right? This whole area is going to pull apart, and this section of Africa is going to be split off. But for now, it's pulling apart at a rate, and a basin is forming. This land is falling here, and some areas are below sea level. There aren't as many lakes in this region simply because it is so dry in some of these areas that a lake doesn't actually even form in the basin, at least not a permanent lake. Here's an area in the East African Rift where you can see for scale these people standing besides this crack in the earth. Now, this crack has actually been kind of like widened by the fact that there was a gaseous volcanic explosion, right? You know, there's a whole bunch of gas exploded and thrown material out of this rift, but that's because it's a rift, right? And so as it's separating, you have magma that's actually not, the magma in the crust below isn't really that far away here, right? And so it has an opportunity to come up and interact with the surface. And so sometimes you have volcanic activity. There actually is quite a few volcanoes in this rift zone. And you notice that all these little red arrows here are all volcanoes, right? So you're often going to have volcanoes in these rifting areas. But in a way, you're actually looking right here, right at the rift. Right? It's cracking apart. The earth is literally cracking apart right here. And then as areas in this whole region crack apart, the whole area is tending to erode down and fall down farther below sea level. All right, so let's address I'm going to say the elephant in the room here. If you adhere to the young earth creationist view, I admit you might be feeling a little bit skeptical right now, right? A little bit concerned. After all, we're talking about processes that I'm saying take millions of years, which is far longer than the proposed 6,000 year age of the Earth that the young Earth models, must have. So it's important to remember that this evidence for long-term processes isn't just based on a single line of evidence. And that's why this series is going to be multiple episodes long, because we're going to look at other forms of evidence. And it's really the accumulation of all these forms of evidence that makes such a compelling case for the origins of this region being something that has been in the making for a long period of time. But here so far, we've talked about GPS, radiometric dating of rocks, independently confirming each other's values, paleomagnetic data, which I didn't cover, but is in my paper. We're eventually going to talk a little bit about thermochronology. And then we're going to look at the actual time to actually form the sediments and form the salt crystals themselves, right? We're going to do a whole chapter on that. So I'd say each of these methods is going to point to the same conclusion, that conclusion that the Earth is indeed really old. And the Dead Sea transform has been active for millions of years. We have the offset of material on either side of the fault for many, 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 many miles, suggesting this fault has been active for long periods of time. We're going to have thick layers of sediment in the basin we need to explain. We're going to have magnetic signatures in the rocks that point to their experiencing changes in magnetic fields over millions of years. Right? All these things are going to fit a old Earth view and present a very significant challenge to the young Earth view. Now, some young Earth creationists have attempted to explain the formation of the Dead Sea as a catastrophic event. Right? They would say like, okay, yes, I mean, clearly there is a rift there, right? And it's a basin, and how do basins and these rifts form? Well, you have a fault and this rock, I can see that these rocks on one side, like these rocks down here at one point were down here. They're supposed to be across from this. And now they're slid all the way up here. And so you've slid that thing up 60 miles. That's a whole long way to go, but maybe that happened very, very quickly. Like at the end of the flood, boom, they just all slid up there. And then now they've almost stopped, even though they're just barely moving today. That would explain why the radiometric dates suggest they've been sliding at a constant pace for that long a period of time. But nonetheless, you could say like, well, they've just happened really fast. But there really isn't any known mechanism for making that happen that quickly. Then you also have to have the basin form. That basin has to then fill with sediments. Where did those sediments come from in such a short period of time? It's very difficult to reconcile this with catastrophic formation in just a few thousand years, or as I'm going to show you, you're going to need a lot less than time than that. a couple hundred years ago? Why do you think I've been emphasizing the fact that Lot and Abraham 4,100 years ago, just 400 years after global flood, were looking down into this valley and pretty much saw what you and I would see today if you were there in terms of the geological formations, suggesting not much change has happened. So that's going to compress all the events to create this land and this place into exceptionally short periods of time for the young earth creationists. But this creates another problem, and I did want to spend just a little bit of time talking about it in this episode. This idea of catastrophic plate tectonics, that plates have moved very, very rapidly over very short periods of time in order to get to where they're at today, but still have all the material that was laid down on Earth happen during a global flood. So you're limited to this very short period of time. It creates another really significant problem that has been talked about by many people before, but I thought I would take an opportunity here to emphasize it as well. The amount of heat that would be generated by these plates moving past each other at the speeds that would require to form all the Earth's current geography, right, would literally boil the oceans and melt the Earth's crust. And it's not just the heat of friction. It's the fact that there are massive volcanic provinces. There are volcanoes in the Dead Sea Valley, right? There's volcanic rock. And there are layers of volcanic material in the upper regions of the sedimentary column. And so you have to account for where did that volcanic material come from and how do you dissipate that heat? So it's called the heat problem. And it is a really serious problem for young earth creationists that have been, and many of them been trying to grapple with this. And they will freely admit it's an unsolved problem at this point in their model. How would they get rid of the heat that would be generated by all the events that have to occur in a very short period of time? I really do recommend two videos by the Guts of Gibbon channel. She's done a wonderful job of doing the calculations, of confronting creationists and others and really testing their models. And so these two videos, which I'll link at the bottom of this video, are really some of the best in terms of like outlining the problem and dealing with the arguments that young earth creationists have tried, or their possible explanations that they have suggested. I mean, this has been a problem for some 20 years. I mean, this was pointed out a long time ago. I mean, Dr. Baumgartner, a young earth creationist, in 2003, when he calculated and he kind of came up with this idea of catastrophic plate tectonics, that the plates could have during the end stages of the flood, after all the sediments were laid down, because after all, a lot of plates have separate the entire geological column and move the whole geological column. So therefore, it kind of stands to reason the entire geological column, or most of it, would have to have existed prior to the plates moving. So therefore, it has to happen at the end of the flood or right after the flood. And so he came with this idea that the plates quickly moved, like North America and South America moved away from Europe and Africa, during that time. Well, that's thousands of kilometers of motion. We're not even talking about nearly that much in this particular region. But his own calculations of his own model suggested that in order to have that kind of motion in that many different places on the Earth would vaporize the Earth's ocean and probably melt a significant portion of the crust and mantle. So we wouldn't have sedimentary rock. It'd be all metamorphic. So another way to think about it is the heat that's generated by plate tectonics, right? In addition to potentially accelerated radioactive decay, because young earth creationists also try to explain why do the radioactive dates suggest the Earth is really old. Well, maybe there was a accelerated decay in the past. Well, that also creates heat, right? So it's compounding, and there's lots of volcanoes, lots of volcanic material that all would have had to been spewed all around the same time. And so all of that combined creates incredible amounts of heat. So, and I touch upon this in much more detail and give some other examples from the young earth creationist literature in the paper that's associated with this particular talk that's on my blog site, thenaturalhistorian.com. All right, this episode's running a little long. I wanted to keep these a little bit shorter than my usual stuff, and here I am still going at an hour. Yeah, the Dead Sea transform. It's, I think, a testimony to the dynamic nature of our planet. Right? You can really see plate tectonics here, and you can see what it's done to the land. Right? This deep rift valley, it's got this super salty waters, the Dead Sea. Every feature of this area just reeks of millions of years of geological processes. And as we've seen, the evidence for a long-term gradual development of this region is overwhelming. I mean, that's the really important part is just none of this stuff can just happen instantly. And that'll become very apparent when we look at the salt layers that we're going to need to explain. So it comes from multiple independent lines of evidence. They all point to the same conclusion. And I think this is a huge challenge to traditional interpretations of scriptures. So before we ask how biblical literalists really do attempt to squeeze the evolution of the Dead Sea Basin into just 4,500 years, and as you've heard me say before, it's not really 4,500 years. It's really just a couple hundred years, right? All the things that have formed the Dead Sea have to have formed within a few hundred years, because Abraham and Lot, tell us that everything that we see has been pretty much the same as it's been for the last 4,000 years. Right? We have to explore one other really big question about the big picture of the history of the Dead Sea. And we need to know whether this valley, the Jordan Valley, has this valley ever been filled up with water? Right? Has it ever been filled up with water? We've been talking about how the water is going down, 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 down. The Dead Sea is getting deeper and deeper and deeper, lower and lower and lower over time. But has it ever been full of water? And what would be the implications of that for explaining the origins of this region and the sediments in this region? So in our next installment, we're going to travel back in time to explore something called Lake Listen. All right. That's the Pleistocene age precursor of the Dead Sea. We're going to see how this ancient lake is going to provide us some really crucial evidence to understand past climate changes in the region. And we're going to see how its history poses a really significant challenge to flood geology models. We combine the depth of the geological column below the Dead Sea, the salt layers below the Dead Sea, but the fact that there are layers of sediment that are lake sediments that go all the way up the sides of the valley, tell us that there was a huge lake there at one time. We got to ask the question, when was that? When was the Jordan Valley one giant lake? We've got that coming up in the next episode, part 4, Lake Listen, the Jordan Valley underneath water, including the Sea of Galilee. Thanks for hanging out with me. Talk to you next time. Thank you for watching this installment of the Dead Sea Chronology series. As we've explored today, the Dead Sea region provides fascinating insights into Earth's history and raises important questions about how we interpret both scientific evidence and scripture. If you'd like to dive deeper into this topic, I invite you to visit my blog, Naturalis Historia, at thenaturalhistorian.com, where you'll find detailed articles exploring each aspect we've covered today, including full references and additional resources. Here's the schedule for upcoming episodes in this series. Each new video builds on what we've learned today, helping us better understand how geology and questions of the Earth's and our origins intersect in this remarkable region. You can learn more about my work and background at joelduff.org. If you found this content helpful, please consider subscribing and sharing with others who might be interested in exploring these important questions about science and faith. Thank you again for watching. Blessings to you and all who are around you.